Section 4.3 talks about spanning sets. So spanning is pretty much like multiples. You know, we start with, I'm going to show you a geometric interpretation of it. What it means is mul. So the span of a set is pretty much all of its multiples. If W is a vector in a vector space V, and then W is said to be a linear combination of these vectors, if you could find W to equal some multiples of those, these are constants or scalars, and these scalars are called coefficients of the linear combination, meaning if W is a vector in a vector space, we have this W. If I could figure out a way of picking vector space consists of V1, V2, V3, to V sub R, where R is less than R sub n, whatever that is. If I could take multiples of those, K1, or say, A times V1 plus K times V2 plus K sub R, V sub R. So if I could find these coefficients right there and have them equal to that, we say this W is a linear combination of those. And I'll show you a few examples. Recall that, and this is something for you to know. The unit vectors in Rn would be E sub 1, 1, and zeros all the way down. And E sub 2 will be 0, 1, 0 all the way down, and so on and so forth. So if I go with R2, we claim that 1, 0, 0, 1 pretty much spans the whole space. Any point, any vector you find me in R2, let's say you said, well, let's say the point 3, 7, or you say the vector 3, 7. I'll say, okay, that's easy. Call this V1, call this V2. I'll say take 3V1 plus 7V2. That will give you that point, or the vector. That will be 3, 0 plus 0, 7. That will be 3, 7 if it's a vector, and if it's a point, make it a point, 1, 0, and 0, 1. Multiply this one by 3, and this one by 7, and add them. There it is. So, any linear combination of those two indicate that I could multiply this by a constant, this by a constant. In this case, it was the 3 and the 7, to get whatever number you provide. So 3, 7 is a linear combination of 1, 0, 0, 1. And of course, for R3, it is 1, 0, 0, 0, 1, 0, and 0, 0, 1. That spans pretty much everything, or all the vectors / points in that vector space. Now, a procedure to identify spanning sets. Spanning sets is multiples. It's a bit confusing in the beginning. Let S be consisting of those vectors. Be in vector space V. Let's say X is some random vector in V as well. Set up an augmented matrix. So when you're going to solve it, set them equal. Say, let's find set K1 times W1, K2 times W2, all the way to K sub R, WR, set equal to those. And if you could find a solution, that means X is a linear combination of those vectors. If you can't find a solution, you'll say, well, it's not a linear combination of those, and it's not in the spanning set. Use techniques developed in chapter 1 and 2 to investigate the consistency or the inconsistency of the system. If you have a consistent system, whether it's one solution or an infinite amount of solution, then we say the vectors in S span V. And if it's inconsistent for some value of X, we say they do not. That's simple. That's how you know if they span or not. Well, let's see. Let's look at an example and see how this works. So, in this vector space, we have the following 3 vectors. They give us a vector right there, and they say, hey, is this a linear combination of those three? It could be, it could not be. So let's say you take A times U plus B times V plus C times W, where A, B, and C are scalars, and set them equal to -9, -7, -15. Well, how does that work? A times U1, again, now I'm going to do the first problem only the long way. I'm going to do it here on the side. A times U1, that would be 2A, A, and 4A, plus B, V, that would be B, negative B, and BB, and I'm putting them like that on purpose, plus C times W, that's 3C, 2C, and 5C, right? Well, if I really want to go ahead and put them up, and I want to see if those are equal to -9, -7, -15. Well, think of it this way. Wouldn't the column for A be 2, 1, 4? Wouldn't the column for B be 1, -1, 3? And the column for C would be 3, 2, 5? And that's a -9, -7, -15. Isn't that the system that I'm solving? Or I could say, if I really want to write it out, 2A plus B plus 3C and A minus B plus 2C and 4A plus 3B plus 5C equal -9, -7, -15. And wouldn't you set the I component equal to the I component, the B component equal to the B component, or I mean I, and the J component equal to the J component? Isn't that how things work? So instead of doing this every time, and since we're going to do that a lot, it's best if you jump straight from the vectors and just list them out. So 2, 1, 4, that's the A. 1, -1, 3, and 3, 2, 5. Set it equal to -9, -7, -15. Now there are multiple ways you could figure out whether there is a solution to this or there isn't a solution to this. One way, figure out the determinant of this matrix. If they're just asking, is this a linear combination or not? If the determinant of this does not equal 0, there's a solution, therefore it's a linear combination. So whatever you learned prior to this, you could use. You could use power reduction. You could say, you know what, let's solve this problem. You know, no big deal. For example, you could say I'm going to do both ways for this. It's up to you how you do this. Take -2 row 2 plus row 1. Put the result in row 2. And take one way of doing this. And take -4 row 2. Add it to row 3. Put the result in row 3. So basically we're making those zeros the first round. So that's one way. Now if they say find the solution, if they say, oh, I'm sorry, they didn't say figure, they say express the following as linear combination. So you have to find it. In this case, I don't have a choice. But on other problems that are coming up, they're going to say, is this vector a linear combination of U, V, and W? If they ask you for that, well, hey, I can just figure out the determinant of this if I want. Again, if it doesn't equal 0, that means there's a solution. And if there's a solution, then guess what? It is a linear combination. But if they want me to find it, I'll go ahead and find it. Multiply this by -2 and add it to 1. That's 0. 2, that's a 3. And -4 plus 3, that's a -1. Oh yeah, we left it like that, right? Okay. So multiply by -2. Let's see. -2, 2, -4, add it to row 1. That is 0, 2 plus 1 is 3, negative 4, and 14 minus, is that a 5? 5, I think, okay. And multiply row 2 by a 4, negative 4, that makes it negative 4, 4, 8, and negative 28. Add it to this row. That would be 0, 7, 13, and negative 20, 30, 43, sorry. Yeah. And the next step is to make that a 0. So I could take, and of course you can do this in so many different ways. I could take 7 times row 2 minus 3 times row 3, put the result in. Hopefully I didn't make a mistake, and if I did, I'll go back and fix it. So if I multiply that by 7, that's 0, 21, negative 7, and 35. Multiply this by negative 3, 0, negative 21, negative 39. Oh boy, and a 3. That's 3 times 43 times 3. That's 9, 129, positive. And if I add those, I get a 0, 0, that's negative 46. And if you add those, 14, 6, 164. Okay, check those numbers. I found a mistake. It was right here. Back, so when we did those, multiply row 2 by negative 4, that makes it a negative 4, a 4, and negative 8, and a positive 28. Yeah, the numbers, it does something that look right. Okay. So if I was to add those, what would happen? I'll get a 0, a 7 still, but I'll get a negative 3, and I'll get 28 minus 13. There you go. And I'll do the same thing right like we did, but now the numbers are going to change slightly, because when I add those, I'll get a 0. Where did I write it? I thought I wrote it somewhere. Okay, let me do it again. Oh boy. Okay, sorry about that. So multiply by a negative. Oh, here. Multiply by 7 row 2, that's 0, 21, 7, negative 7, 35, and multiply by a negative 3. There you go, much better. 0, 0, and that's a 2, and that's a 4. Negative 4, if I'm not mistaken. So A, B, C. So C is, if 2C equal negative 4, that means C is a negative 2. Go up 1. 3B plus 2 equal 5. That means 3B equal 1. And 2A plus B, that's 1. Minus 6 equal negative 9. So that makes it a negative 5. That makes it a negative 4. So A is a negative 2. So basically all of this work, what we got to is, if you take negative 2 times U plus V minus 2W, you will get the negative 9, negative 7, negative 15, which means that's vector is a linear combination of those three. That's what linear combination means. And I hope this clears it somewhat. And of course, if we'd like to find those equaling 0, well, that's really simple, because in that case, I'll just take the 0 times U plus 0 times V plus 0 times W. That is definitely 0, 0, 0. That's really quick and simple. Very easy to show. I don't have to solve any of those or work out any of those. So you know that I can get with ease. Of course, you can set them and solve them if you want. That would be 2, 1, 3, 1, negative 1, 2, 4, 3, 5, 0, 0, 0. Now I'll elaborate really quick on why you should work smart, not hard. could do the same thing, the same mark, but what's the worst that could happen? The worst that could happen, this row could zero out altogether. If it's zero out, that means I have an infinite amount of solutions. Hey, that's a solution. That means it's a linear combinations. And if I get a number right there, then I could say that that's zero, that means that's zero, and that's zero. The only part you really want to, the only part that you might want to check is actually by plugging them in if you want. But you know, you could solve that, and you're going to get the same thing. Again, the only way that's what I would say. The only way I'll get no solution, if I happen to have 0, 0, 0, and a number, say 3. Then you say 0 cannot equal 3. But as long as that is a 0, either you get one solution, or you get an infinite amount of solutions. Either way, that's a solution, and therefore this will be the linear combination of those. That's fairly simple to do. Alright, now we're going to move to the next idea, and let's see how this works. Again, linear combination is a big deal. This book takes it fully in depth, which is really good. Normally they just talk about it theoretically. Let's see if this works. In each part, determine whether the polynomial is a linear combination of P1, P2, P3. Okay, well, let's see how this works. If I want to take 1 plus x, that's a linear equation. So can I take A times P1 plus B times, we're going to use A, B, and C for quadratic ax squared. Okay, that's okay. Let's stick with this. P2 plus C P3 and set it equal to equal let's go with 1 plus x for now. So basically we're saying if I take A times if I take 2a plus ax squared plus bx minus bx squared plus c plus 2cx equaling 1 plus x. Wouldn't you will collect all the constants 2a, b doesn't have plus c plus a plus b plus 2cx, and the square term will be a minus b x squared equal 1 plus x plus 0 x squared, right? Wouldn't that mean you're looking at, for the column of A, you'd be looking at 2, 1, 1. For the column of B, you'll be looking at, yeah, I can't. That's a B, not a BX. If you multiply this by B, that's B minus BX squared. So the constants, there's a plus B there. So that will be A, which is 1, no B, and the B column here, there, much easier. I'm going to keep looking back and forth. B is right there. There's no B there and a B there. And C, okay, there's no C there. So now it's easier to see. So that's 1, 0, negative 1, right? And for the C, I have a 1. There's 2 right there, and there's a 0 for the third. There we go. And I want that to equal to what? Well, let's see. I want the constants to equal to 1. the x's to equal to 1 and the squares to equal to 0. There. And I could have skipped all of this work and not did any of this work whatsoever by simply taking the coefficients of those 2, 1, 1, 1, 0, negative 1, and 1, 2, 0. There you go. With ax squared plus bx plus c, but we're going backwards, doesn't matter, it's the same thing. Right? And set it equal to constant a, b, and a 0x squared. And skipped all of that work. Either way. Now here, notice they're not saying find. If they say find, you have to do the work on a, b, and c. But here what they're saying, in each part, determine whether the polynomial is a linear combination. Is it or is it not? Now, do you agree that whether I do this on A, on B, wouldn't I copy this identically? Wouldn't I copy that identically? And the only thing that will change would be here I'll have 1, 0, 1, and here I'll have 1, 1, 1. But do you agree that the colored matrix is the same? So if I'm only looking, again, if they say find the weights, that's what they call them, weights. If they say find the weights, you have no choice other than solving. But if they say are they solutions, well, hey, why don't I figure out the determinant of 2, 1, 1, 1, 1, 0, negative 1, 2, and 0. And if I want to figure out the determinant, remember the shortcut for a 3 by 3, that will be 0 plus 2 minus 1 minus 0 minus 4 plus 0. That would be 1 plus, that would be 5, which doesn't equal to 0, which means there is a solution. So yes, yes to all of those. Yes, 1 plus x is a linear combination of those. 1 plus x squared is a linear combination of those, and 1 plus x squared is a linear combination of those as well. So it's enough for me just, if I want to know if there's a solution or not to do any of this work, just take those and say, look, 2, 1, 1, 1, 0, negative 1, and 1, 2, 0. That's the matrix, that's the coefficient matrix. If the determinant of that equals 0, there's no solution to any of those. And if that determinant doesn't equal 0, there is a solution. So again, this is where the theory is going to start kicking in, and you no longer have to do the busy work of just calculating things left and right. If they say, find the solution, you have to do a lot of work. If they say, is there a solution? Well, that's what linear algebra is all about. I want to do number 5 because number 6 is another polynomial. And number 7 is another matrix. So I wanted to do a matrix. So I'm going to give you, you'll see the homework. I'm going to give you number 6 on the homework, and I gave you the answers. So let's look at 5. What if they give us a matrix and say, in each part, express the vector as a linear combination? Okay, here they want it to be linear combinations of each other. Okay, well, let's see how we're going to express this. Here we have to find them because they're saying, not saying is there a solution or can it be? Well, in each part, express the vectors as a linear combination of, and here we are, we're talking about those two vectors, linear combination of those 4. So basically what we're being asked to do is, can you take, and I could use letters A, B, and C, but with capital letters that will be a problem. Can you take K1A plus K2B plus K3C plus K4D and have it equal, call this L, matrix L? Well, let's see how that works. Again, I could do all the work and put all of those in, or I could simply say, well, look, if you're going to multiply K1 times A, right, that's going to be 1, negative 1. Actually, I should show you this. No, this one I should show you for sure here. Let me do it on the right. So if I multiply K1, what we're saying is K1, negative K1, 0 to K1, plus 0 K2, 0 K2, plus 0 K3, 0, 0, plus 2 K4, 0, K4, negative K4. If I add those, don't you add component to component? Isn't that K1 plus 0 plus 0 plus 2K4? Wouldn't this be negative K1 plus K2 plus K3 plus 0? Wouldn't that be 0 plus 0 plus 0 plus K4? And wouldn't that be 2K sub 1 plus K sub 2 plus 0 minus K sub 4? And you're going to set those equal to 1, 2, 2, 4. Which would mean I want those to equal a 1, and those to equal a 2. I want K1 plus 2K sub 4 to equal a 1. I want negative K sub 1 plus K sub 2 plus K sub 3 to equal a 2. I want K sub 4 to equal a 2. And I want 2K sub 1 plus K sub 2 minus K sub 4 to equal 4. So here, if I put the K's in order, that's 1, negative 1, 1, and actually that's not a 1. That's a 0. That's only K4, right? So if I line them up, and for K sub 2, so here, let me not lose track. K sub 2, there's no K sub 2, there's K sub 2, there's no K sub 2, and there's K sub 2. So that will be 0, 1, 0, 1. And for K sub 3, that one doesn't have it. There's a K sub 3 there, that one doesn't have it, that one doesn't have it. That will be simply 0, 1, 0, 0. K1, 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 and 2. And of course, the last one, K sub 4, tell it is 2. There's none here. There's 1 here, and there's negative 1 there. And that will equal 1, 2, 2, and 4. How can I figure that one out? Well, pretty much you end up, since that's going to be multiplied by K1, you put them in order 1, negative 1, 0, 1 right there, and then 0, 1, 0, 1 in that order, 0, 1, 0, 0, and 2, 0, 1, negative 1. Again, you'll get used to this. Now, we're not going to do this a lot, but I want to solve that equation if I can. And if I could solve it, then there'll be a solution. Otherwise, it's an issue. Well, let's see how that works. If I row reduce this, I end up with, and I did this on my calculator, 1, 0, 0, 0, negative 3, 0, 1, 0, 0, a 12, 0, 0, 1, 0, a negative 13, and a 0, 0, 0, 1, and a 2. And that tells me what the weights are. That tells me K1 is negative 3, K2 is 12, K sub 3 is negative 13, and K sub 4 equal 2, which means I could plug those in right there. And I could say, if you take negative 3 times 1, negative 1, 0, 2, plus 12 times 0, 1, 0, 1, minus 13 times 0, 1, 0, 0, plus 2 times 2, 0, 1, negative 1, and that should equal a 1, 2, 2, 4, and you can check the work. And again, these are a lot of work to do those. Now, if I wanted to know only if they have a solution or not, I'll figure out the determinant of this. Oops, not this. I'll figure out the determinant of this matrix, right? And remember, this is a 4 by 4, so I could pick this row. That'll make life really easy. And that's not going to equal 0 because I didn't get a solution. And you'll notice if I just want to set up B, I'm not going to work out B because that's a lot of work. If I just want to set up B, well, hey, A is not going to change, but just for practice, to set it up, instead of doing all of this work right here, I could just say automatically, I want to solve the system, and again, this is K1 plus K2 plus K sub 3 plus K sub 4, and K1 is going to end up being 1, negative 1, 0, 2, 0, 1, 0, 1, 0, 1, 0, 0, and 2, 0, 1, negative 1, and that's going to equal 3, 1, 1, 2, and see if I can solve that. And again, here it turns out to work out really smoothly. It turns out to be all ones. And again, you can do that in a calculator, which means multiply this by 1, this by 1. So if you just add those, add 1 plus 0 plus 0 plus 2, that's a 3. Add negative 1 plus 1, that's a 0, plus 1 plus 0, that's a 1. Take 0 plus 0 plus 0 plus 1 is a 1. And 2 plus 1 is 3, minus 1 is 2. There you go. So the weights turn out to be K1 equal K2 equal K sub 3 equal K sub 4, which is a 1. All right. And I want to move to number 10. And it's asking, determine whether the following polynomials span. Okay, well, they're not saying find, which is good. Basically, what they're asking us to do. Now, what's P2? P1 is ax plus b, that's a linear equation. P2 is quadratic, ax squared plus bx plus c. Cubic is ax cubed plus bx squared plus cx plus d, and so on and so forth. So in this case, they're saying, well, look, can you multiply this by some k sub 1, this by k sub 2, this by k sub 3, and this by k sub 4, and set them equal to that, and solve? Could that work? Well, the matrix is going to look like what? If I look at P1, it's going to be 1, 1, 0, and here we have 1, negative 1, 0. Here we have 1, 1, 1, and here we have 2, 0, negative 1. And we want to see if constants. So see the constants b and a. We want to know if this has a solution. Again, determine whether the following polynomials span this. We just want to figure out, is there a solution to this or not? Well, let's see. We could solve it, or we could just figure out the determinant of this and see how that works. There are 4 of them, I see. So that's K1, K2, K3, K sub 4. This has an infinite amount of solutions, right? We have more columns than rows. Okay, let me see if I can put this in the calculator so we get this. Okay, this does have a solution. Well, here, let's find it anyways. Might as well. So let's ignore that. Let's reduce this. Yeah, I got the determinant of that, and that's not 0, so there's a solution. So if I make that a 0 on the first attempt, take, this is simple, negative row 1 plus row 2 in row 2. I'm looking at 1, 1, 1, 2, and a C. I'm looking at 0, 0, 2, 2, and B plus C. Yeah. and then 0, 0, 1, negative 1, and an A. Okay? I don't need to be that big. And now, if I want to make that a 0, I'll take row 3 times negative 2, add it to row 2, and row 2. So 1, 1, 1, 2, and a C. 0, 0, 2, 2, B plus C. If I multiply this by 2, that's a 0, 0, 2, negative 2, and 2A. And if I add them, I'll get a 0, 0. Time out. But by negative 2, that's negative, that's positive, that's negative. That'll give me a 0. That'll give me a 4. And that'll give me a negative 2A plus B plus C. As you see, there is a solution, right? We have 4 of those. You can say k sub 4 can be a negative 1s. This is, this k sub 4. So here, k sub 1, k sub 3, k sub 4. You can say k sub 2 could be whatever it wants. But there's a solution, so yes, we conclude that. Yes, determine the following span. Yes, P1, P2, P3, and P4 span. We actually need to put polynomials, span P sub 2. And if there's no solution, span. And there's the